Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Sebastian Garcia-Saenz. He received his PhD in 2016 from Columbia University, and since 2021, he is an assistant professor at SUSTech. Thank you, Sebastian, for agreeing to give this talk. The stage is yours.
Thank you very much, Torben, and all the organizers for this wonderful opportunity. So today I'll be talking about this work, not new by now, from last year, but I will also say a little bit, time permitting, on a follow-up that we have coming out hopefully very soon, the next month or so. So this is work I should acknowledge my postdoc Shuwen and my student Alfei here at SUSTech. And my slides are not moving. Oh, there it is. So this is the plan. There's a lot of jargon here you don't need to understand at this stage, but basically to set the stage, I will be mostly talking about vector fields, more specifically vector tensor theories, and in the context of black holes. So this is going to be the context of the talk, just to set the stage. So the sort of question I would like to use to motivate this talk is the following. Under what conditions do black holes in general relativity can grow hair in the form of a massive vector field? So this is sort of the broad question I would like to address today. Hopefully I will convince you that this is a well-defined question. It's a question that we can tackle. It's a question that, in fact, we have partially answered already. And second, I also hope to convince you that it's an interesting question. So to try to sharpen the question a little bit, I can rephrase it as follows. So can we have a control transition? And I will try to explain what I mean by control from a state given by a GR black hole solution and a hairy black hole solution in one of these vector tensor theories. So that's the question. So trying to motivate this, hopefully to this audience, I don't need to motivate hairy black holes, but I'll do it anyway in 1 minute. So we understand why hairy black holes are interesting. First of all, they provide a way to test deviations from GR, a very clean way to test deviations from GR, thanks to the famous no-hair theorems of Bekenstein that says that in GR and with standard enough matter fields, black holes should have no hair. Okay, so by hair I mean, for the people who are not familiar with this, some kind of field profile in the exterior of the black hole that is stable, should be stable and stationary. So this is what I mean by black hole hair. We also understand that hairy black holes are interesting laboratories to test new physics primarily in the form of new light particles. So this is the program of black hole spectroscopy that's well developed by now. And also from a more theoretical perspective, hairy black holes are also interesting formal systems, for instance, in the context of ADS-CFT, as duals of condensed matter systems, for instance. So as you probably know, hairy black holes are most often studied in the context of scalar tensor theories for several reasons. First of all, scalar tensor theories are, of course, the most minimal kind of modification of gravity that you can think of. So this minimalism allows you to have good analytical control, which is always good. Related to this is the fact that by now we understand these models quite well. So the space, there's been throughout the past almost 2 decades now, this very interesting program about classifying scalar tensor theories, which is essentially complete at this stage. So I'm thinking about Horndeski theory and beyond Horndeski theory and so on. For me personally, the main motivation to study scalar tensor theories is that they provide us models of dark energy. So for most of us, this is the main motivation to study modifications of gravity, and scalar tensor theories are successful in that respect. Now, in the context of black holes, they are also interesting because they provide a mechanism to form hairy black holes. So not only do hairy black holes exist in this type of theories, so they can evade the no-hair theorem of Bekenstein, but we also have a mechanism to actually form these black holes starting from GR solutions. So this is the famous mechanism of scalarization, which is by now well understood. There are many variants of the scalarization mechanism. I don't need to review this here. But basically, this is by now well understood, both at the analytical perturbation theory level and also at the full nonlinear level. So here I'm showing, just to brag a little, a numerical relativity simulation that we did in our recent work. So this is full numerical relativity that confirms basically everything that's known in perturbation theory. Now, I also think that there are some drawbacks to scalar tensor theories. So for instance, we know by now that the simplest models don't really work to explain things like dark energy, for instance. There are still more complex models like Horndeski and beyond, but then you can potentially run into other problems. So we know that you can very easily sort of mess up the speed of gravitational waves, which is very tightly constrained. Then you have to worry about fifth force experiments. Then you need to invoke some kind of Weinstein mechanism to suppress the fifth forces. But with the Weinstein mechanism, we understand that there are other issues, such as strong coupling and so on. I also think personally that scalar tensor theories, there's a bit of a Lampos effect here. So maybe we like scalar tensor theories so much simply because they are the simplest kind of theories. They are the theories that we know how to calculate with. So I also believe that there is a bit of a Lampos effect with scalar tensor theories. This is not meant to be a critique, really, of scalar tensor theories, but basically I want to make the case that it might be worthwhile at this stage to start looking beyond scalar tensor theories. So that takes me to the main aspect of this talk, which is next simplest thing beyond scalar fields is vector fields, right? So I also think these are well motivated for various reasons. So we know that they are good candidates for dark energy. They have also been proposed as candidates of dark matter. From a particle physics perspective, light vector particles might actually be natural, so more so than scalar fields. So they don't have the same naturalness problems, not always as scalar particles. And more generally, I think they are at least equally, or perhaps even better motivated for modifications of gravity. Now, what about black holes in this type of theories? In fact, we do know hairy black hole solutions. But the question that is not so clear yet, at least, is how do we form these hairy black holes? Assuming, say, for instance, you start with a GR black hole. So people have proposed direct equivalents of the scalarization mechanism. Very creatively, we call them vectorization mechanism. So what do we mean by vectorization? Sorry, I'm trying to move this window. What do I mean by vectorization? What I mean is the following. So the idea is, can we have a tachyonic instability, but a tachyonic instability without also having ghost and gradient instability? So this is what I will use as my working definition of vectorization. So by tachyonic instability, I remind you what I mean is that you have some kind of effective potential, which in the vacuum state, so with a trivial vector field, you have an effective mass that is a squared effective mass that is negative, so that the vacuum state is unstable. Okay, but again, we don't want this instability to be catastrophic in the sense of also having ghost or Laplacian instabilities. Okay, so this is going to be my working definition of this mechanism of vectorization. Although I should warn you that in the literature you may find different definitions. By the way, since this talk is being recorded, I should apologize in case I'm I'm not citing your work here. This is not meant to be an extensive list of references. So I apologize in advance. So this is the question that I asked at the beginning, and maybe hopefully now it's a little bit sharper. So the question is, can we have tachyonic instabilities without ghost or Laplacian instabilities? And the partial answer is no. So this can be formalized in the following no-go theorem, which is the following: inconsistent, and I will explain what I mean by consistent. Inconsistent vector tensor theories linearize about static and spherically symmetric GR solutions. This is not possible, meaning if you can have tachyonic instabilities, but they are always going to be necessarily accompanied by ghost or Laplacian instabilities. So this is the theorem. In our work in preparation, the one that will appear soon, we can actually generalize this beyond static spherically symmetric. So this assumption about spherical symmetry is actually not essential. So this is in our coming paper. Now, there are other loopholes, of course. So naturally, you may want to consider other backgrounds. So I do think that considering instabilities of GR solutions is well motivated for fairly obvious reasons. But you don't need to make that assumption. You know, you may believe that GR black holes actually don't exist. In nature, maybe all black holes start life as hairy black holes, so that this question, becomes a little meaningless. But that's a possibility. Of course, you might also consider more general theories than the ones I'm considering here, which I will explain in a moment. You can also consider more fields, of course, and so on. And a third potential loophole that I see, which to me is perhaps the most interesting one, and we are also working on this, is about the nonlinear evolution. So in the case of scalar tensor theories, it is known, for instance, that you can have scalarization triggered by nonlinear instabilities while having linear stability. So that's a possibility that's known to occur in some scalar tensor theories. Whether that's possible in vector tensor theories is, I believe, a no. So this is my setup in one equation. So we are going to, I claim that this action gives you the most general, consistent, quadratic in the vector field, vector tensor theory. So this is my claim. So the first line should be familiar, hopefully. I have a standard GR, the Ricci scalar here. I have the Maxwell term. And then I have my Proca field. So this is not, you should not think of this as the photon. So this is meant to be some additional vector field in the theory that has a mass, an explicit mass. So this is the first line is simply the Proca theory minimally coupled to gravity. Now, it turns out that you can consider, still at quadratic order in the vector field, you can consider two types of couplings to the metric, which are non-minimal. So one involves the double dual Riemann tensor. Double dual means two contractions with the epsilon tensor. So this is parity even, I should say. You have two epsilon tensors. And then you can also have a coupling to the Einstein tensor. Okay. So the claim is that this is the most general theory that you can write down at quadratic order in the vector field on a general metric background. So this is fully nonlinear in the metric, which is consistent in a sense that I will explain in a moment. So this we proved here. I'm acknowledging the work of Horndeski. It's an old work of Horndeski. So this we proved a few years ago in 2022. But I like to acknowledge Horndeski because really our proof is almost a corollary of his construction, the construction that he did for a massless vector field. The generalization to a massive vector field that we did is really almost a corollary of his work. So I think it's worth acknowledging Horndeski. So this can be demonstrated from a bottom up. So one can do like a brute force analysis and prove this, but it can also be alternatively derived from a kind of top down approach. simply by looking at all the known fully nonlinear vector tensor theories on the market. So I'm thinking about theories like generalized Proca, Proca Nuevo, generalizations of these theories like extended Proca Nuevo, beyond generalized Proca. Your favorite vector tensor theory that people have been looking into for a decade now, to address things like dark energy. The claim is that, so in here here I wrote explicitly the Lagrangian for generalized Proca. The claim is that looks very messy, but the claim is that once you expand at quadratic order in the vector field on an arbitrary metric background, you are going to get this, and you cannot get anything else. That's the claim. So finally, what do I mean by consistent? By consistent, I simply mean 3 degrees of freedom and nothing more. So I want this theory to describe a massive spin 1 particle coupled to gravity, but nothing else. So this is going to be my working assumption. If you are an effective field theorist, you might say this is not necessary. Fair enough. Take this as a working assumption I'm making. Okay. Why quadratic order? Remember, we are interested in the linear stability of GR solutions. So I don't want tadpole terms here because I want GR solutions to be solutions of this theory. And I don't want to consider higher than quadratic because I'm interested only in linear stability at this stage, okay? And for most of this talk, I will be focusing on spherical symmetry. So this means Schwarzschild or Reissner-Nordström. I will say a little bit about Kerr, but not too much because this is the work that we are wrapping up currently. By the way, I can also add some standard matter if I want. So in the case of a Reissner-Nordström black hole, I will do that. So, but let me start with the simplest case. So the first thing you can do to analyze the stability of this theory on a given background is to look at the Icona limit, equivalently the high frequency limit or short wavelength limit. So this was done a while ago in the context of generalized Proca. We revisited this a few years ago in this more general context. And the results are the following. I will spare you the technical details, but the results are the following. This is basically the no-go theorem I already mentioned, that if you demand the absence of ghost or gradient Laplacian instabilities, then this necessarily implies the absence of tachyonic instabilities. So according to my definition of vectorization, this means that you cannot have vectorization for GR solutions for this type of theories. So this is the first result. Now you can ask a kind of reverse question. Okay, I don't care about vectorization, but I do care about this. I do care about stability. So you can now flip the question. You can say, well, let me demand stability, and then it turns out that you can use these conditions to put bounds on the coupling on the non-minimal couplings. Now you can ask, okay, can I have a window for these parameters so that everything is stable or nice? The answer is actually no. The answer is that you can always find black hole solutions that will violate these bounds. Okay, so this is the second result. So let's illustrate this with the simplest case. So I'm going to consider a Schwarzschild black hole. For a Schwarzschild black hole, remember there are 2 non-minimal couplings. Maybe it's worth coming back for a second. So these are my 2 non-minimal couplings, one with the Riemann tensor and one with the Einstein tensor. For a Schwarzschild background, the Einstein tensor vanishes, so that doesn't show up. So I only care about this first non-minimal coupling. Then the result is the following, demanding stability of perturbations. Remember that we are considering the Icona limit. I will say more about that approximation later. So demanding stability everywhere in the black hole exterior gives you this bound on the coupling constant alpha. So this is a window of allowed values of alpha. But the interesting thing is that this bound is not only on alpha, but it's on the ratio of alpha divided by the Schwarzschild radius of the black hole to the second power. So the implication is that given any non-zero alpha, then you can always find a black hole that's small enough, m small enough, so that you will violate this bound. So this is the implication. Okay, we can put on some numbers here to see if this bound is actually interesting. You may say, well, I don't want all black hole. I don't want black holes to be arbitrarily small, so maybe this doesn't matter. Well, let's see. We can put in some numbers. So here I take an example motivated by theories of dark energy. So so alpha is dimensionful, so it has units of some energy scale to the power -2. On dimensional analysis grounds, I take this scale to be the typical scale of dark energy that is typically shows up in models of dark energy, which is this combination of the Planck mass and the Hubble constant. And if you substitute numbers, you find alpha in units of distance, 10 to the 3 kilometers. So if you substitute in this bound, you reach the conclusion that in this setup, stellar mass black holes would be unstable. Stellar mass black holes have a Schwarzschild radius of order kilometer, but supermassive black holes would be stable. Okay, so this is just to show that this bound can actually be potentially relevant for astrophysical black holes. So if you want to find bounds on the second coupling, we need to consider something that's not a vacuum black hole. So the simplest thing we can consider is Reissner-Nordström. So I should clarify that the electromagnetic field of the Reissner-Nordström black hole that I'm thinking about would be the standard model photon, for instance, which again is not what I have in mind for my Proca field. So this is going to be different vector fields. Okay. So in this case, we can find bounds on the first coupling, which is as function of the charge of the black hole. So here I am plotting stability bounds on the two coupling constants as function of what is essentially the charge to mass ratio of the black hole. So on the left, I have the case of Schwarzschild, which is exactly the bounds that I showed you just now, between 1 and -1/2. And then you find some kind of interesting dependence on the charge of the black hole for the bounds. So what is more interesting here, I guess to highlight, is that now we also have bounds on the second coupling, beta, which I think is interesting because beta, I should point out, beta is dimensionless. So you could say, well, alpha, this is kind of an irrelevant operator. I want to make alpha as small as possible. I don't really care. But this is not true for beta because beta is this is a marginal operator. So beta naturally would be order 1, presumably. So presumably the beta you cannot make it as small as you want. So let's see. Now, if you are a string theorist or something like that, you might be interested in black holes close to the extremal limit. If you are like me, more astrophysics focused, you may complain, well, astrophysical black holes don't have charge, or they have a very small charge. Okay, so let's see. Let us expand these bounds in the limit of small black hole charge. So the resulting bound is given by this inequality here. So this is a bound on the coefficient beta and on the mass of the field. Here, mu, I should have emphasized, I have it here. Mu is the bare mass of the vector field. So this is a bound on the ratio, basically on the ratio beta over mu square as function of in terms of the black hole parameters. So then the question becomes, if you are interested in deriving some bounds of astrophysical interest, you can ask what values of essentially the charge to mass ratio of the black hole could we expect in realistic situations? The short answer is I don't know, but we have a little back of the envelope estimate based on what's known as the Wald mechanism. So Wald, back in the 70s, had this very brilliant idea, which is this brilliant realization that if you put a black hole in a magnetic field, in an external magnetic field, assume for now that the black hole is rotating. So this was the setup studied by Wald. So if the black hole is rotating, then it turns out that the black hole will preferentially accrete electric charges with a sign depending on whether the spin of the black hole is aligned or anti-aligned with the external magnetic field up to some equilibrium value. Okay, so this is called the Wald mechanism. So a little idea that we looked into a few years ago is well, okay. So what Wald had in mind was actually he had in mind a kind of galactic magnetic field, and the black hole would be, for instance, a supermassive black hole at the center of the galaxy. This is kind of the setup that Wald had in mind. What we wanted to study was a more transient situation where you have, for instance, a black hole neutron star merger, a pulsar, say, which gives us much stronger magnetic fields than, say, the galactic magnetic field. So this was we were hoping to get large enough values of the B field so that you can use the Wald mechanism to claim that black holes can become actually sizably charged. Okay, even if only transiently. And we did a bit of a back of the envelope estimate, and we came up with this value of the charge to mass ratio, roughly 10 to the minus 7. At this stage, you might complain that the Wald mechanism was actually proposed for spinning black holes. Here, I'm talking about a Reisner-Nordstrom black hole, so not spinning. Well, it turns out that spin is actually not essential. The really essential aspect of the mechanism is that you should have some kind of relative motion between the external B field and the black hole. So these Chen and Dai, after us, they did a much more careful analysis, and in particular, they did not assume black hole spin, and they confirmed basically this estimate. So that this is a kind of nice proposal. So now with this, we can put in some numbers. So as I said, beta is dimensionless. So naturally, we might expect it to be order 1. Let's take this optimistic value of the charge to mass ratio, and let's take some stellar mass black hole. And then we can flip this, we can turn the inequality I just wrote into a lower bound on the mass of the vector field. This seems like a very weak bound, but if you think about, ultra light dark matter models, so for example, fuzzy dark matter, this bound would actually be relevant. You could actually rule out fuzzy dark matter in this type of theories. Now, to what extent you want to think of these theories as relevant for dark matter, that's a different question. But I'm just making the case that, again, that these bounds could be potentially interesting. Finally, for a Kerr black hole, so this is something we will present in far more detail in the coming paper, but here I just show you some results. So we can find bounds on the first coupling constant alpha. Kerr is vacuum, so the second coupling doesn't play a role. But we find an interesting dependence on the black hole spin. So it turns out that the stability window actually shrinks by quite a lot as a function of the spin. And of course, a large spin is not unrealistic in astrophysics. So this could be a potential way to actually trigger instabilities of black holes through realistic evolution, let's say a merger. So you can imagine starting with 2 black holes which have small spin, but as a result of the merger, the spin increases and you cross the stability threshold, something like that. Okay, so this is something we're investigating. Okay, so all these results so far were derived in the conal approximation, as I said. So it would be interesting to confirm to what extent these results actually persist in a proper kosher full analysis beyond the conal approximation. Okay, so we did this. So the more rigorous analysis to study perturbations on a black hole background is to study the quasi-normal mode spectrum. So we can use quasi-normal modes to diagnose instabilities, as is well known. We do this by looking at the imaginary part of the frequency. So quasi-normal modes are parameterized as a function of time in this way. and you have a boundary value problem, which is not of the Sturm-Liouville type, so your spectrum is not necessarily real. You generically have an imaginary part, and you can use this to diagnose instabilities. So more specifically, negative imaginary part means that the spectrum is stable. Positive imaginary part means that the spectrum is unstable. Okay, so this is what we would like to study, and in particular, whether we can have such instabilities. So doing this, we discover an interesting new effect, which is more generic than the type of couplings I've been talking about so far. We argue that they actually apply very generically to non-minimal couplings involving derivatives of the fields. For simplicity, let me focus from now on a Schwarzschild black hole. So let me start with a toy model before we go back to vector fields. Let me start with this toy model. So this is just a crappy scalar field, but I'm going to consider this weird non-minimal coupling. So this looks weird, but I claim that this is actually kind of the simplest thing that you can consider on a Schwarzschild background. Because we are on a Schwarzschild background, I cannot take couplings involving the Ricci tensor or the Einstein tensors. The simplest thing I can do is to consider 2 powers of the Riemann tensor. So even though this looks pretty contrived, the claim is that this is actually the simplest thing on a Schwarzschild background, on a vacuum background. Okay. So this is going to be my non-minimal coupling that I want to investigate as a toy model. And what we find when we study quasi-normal modes is that the Schrödinger equation that dictates the behavior of the quasi-normal mode spectrum has some poles. Okay, so it has some denominators that can become in principle 0 at some values of the radius. Okay, so this is what I mean by pole. It's a pole that shows up in the quasi-normal mode equation. It is not a physical singularity in any way. Remember that the background here is fixed to be Schwarzschild. Okay, so this is a singularity that simply shows up in the equations for linear perturbations. Okay, so we can study the consequences of having this pole. So first of all, the first question is to ask whether this pole is actually in the physical domain. So here I'm using units where the Schwarzschild radius equals 1. So basically I want to ask if the distance of the pole is outside the Schwarzschild radius. Okay, so this will happen only if this non-minimal coupling gamma is greater than 1/6, as you can see from here. Otherwise, you are in a situation where the pole actually never shows up in the physical domain, so that will not have any consequence, any dramatic consequence. So let us consider this case where gamma is greater than 1/6, so that this is the cartoon. You have the black hole interior from 0 to 1 in these units. Then so 1 is the event horizon. Then you have the pole radius at some value. And then you have the exterior domain, okay? So, sorry, again. So the exterior domain, we call it the pole exterior. So this basically defines a kind of standard quasi-normal mode problem between infinity and this pole here. The region I'm mostly interested in this talk is what I call the pole interior. So the domain between the event horizon and the pole. So this is what we refer to as trapped quasi-normal modes for reasons that will hopefully become obvious in a moment. So if you run again the aconal analysis for this toy model, we find that these trapped quasi-normal modes can actually be tachyonic and stable. So this is the result from the aconal analysis. But now we can actually confirm this through a proper quasi-normal mode analysis. So we did this both in the frequency domain. So we calculated the quasi-normal mode spectrum. So this is the plot of our numerical solution. So here I am plotting, sorry for that. So here I am plotting the quasi-normal mode frequency of the fundamental mode as function of the pole radius Rp. Let me remind you, the pole radius is simply defined in terms of the non-minimal coupling. So this is a parameter that you can tune, that you can play with in your theory. And we find that indeed the spectrum is unstable as soon as you have a non-zero value of the mass of the field. So in this case, the quasi-normal mode analysis does confirm the existence of tachyonic instabilities. Okay. We can also confirm this through a time domain analysis. So this is just to show that these trapped quasi-normal modes are really physical. Physical in what sense? In the sense that they do capture the behavior of the system under time evolution. Just like normal quasi-normal modes, of course. But you might have wondered if these trapped quasi-normal modes really have anything to do with time evolution. The answer is yes. They do give you a good correspondence with the time domain behavior. So here, this is a log linear plot. So a straight line here means exponential growth. So this is consistent with the fact that the quasi-normal modes have a positive imaginary part. So some general lessons we can draw from this toy model, which I argue are generic, and I will expand more on that when I go back to the vector field case. We have a pole in the domain, so this will modify the boundary value problem. Okay, because you need now, if you have a pole in your equation, you need to choose boundary conditions at this singularity, and you want to choose the solution that is regular. Okay, so we would remember that we are assuming linear perturbation theory, so we better not have anything blowing up as at least at the initial condition. And it turns out that this condition actually fixes this fixes the boundary condition at the pole location for the simple reason that the only one solution is regular at the pole. Okay, so you have a boundary condition at the event horizon. This is the usual condition that the field has to be ingoing at the horizon. And now you have a second boundary condition at the location of the pole, which is the condition that the field has to be regular. It should not blow up. So now you have a well-defined boundary value problem. You can solve the problem, find a spectrum, and so on. But the key observation is that this boundary value problem is different from the usual quasi-normal mode problem. The usual quasi-normal mode problem would be ingoing wave at the horizon and outgoing wave at infinity. We don't have that here because the pole does not allow for waves. Okay, you need to choose either something that is regular, finite, or something that blows up. And the physical solution is, of course, the regular. Okay. In the exterior, nothing fancy happens, so we can actually show that these what I call normal quasi-normal modes are actually always stable. So the interesting domain appears to be related to these trapped quasi-normal modes. I can offer some intuition about this behavior of these trapped quasi-normal modes. So basically, you remember that all this happens because we have these poles in the equation of motion of the perturbations. So this pole is actually not hard to understand. Whenever you have some kinetic non-minimal coupling, what you are doing is essentially modifying the effective metric that is seen by the field perturbation. So very schematically, you will have 1 power of the metric from the standard kinetic term, but then you will have some, if you have some non-minimal couplings involving derivatives of the field, then this is going to essentially modify your effective metric in a radius-dependent way. So when you canonically normalize your equation, based essentially isolating box phi, morally speaking, what you are doing is dividing by something that can be 0 at some values of the radius. Okay, so this is kind of the rough intuition of why we have these poles to begin with. Whenever or generically at least, when we have this type of non-minimal couplings involving kinetic terms. Okay. So the claim is that this is actually fairly generic. Now, in this case, okay, this is a scalar tensor, a kind of toy model. I don't really have a good motivation for ever considering this type of coupling. But the observation is that, back to the vector tensor theories, this is precisely the type of couplings that we have in these well-motivated vector tensor theories that people have been looking into for the past over more than a decade, okay? So these are not toy models. So these are actually things that we might have to take seriously. Okay, so this is what I want to argue. So given all that intuition and general lessons that I hope I argued for, we can now look at the actual results for vector tensor theories. So in this case, we have three types of perturbations, unlike for a scalar. So we have a monopole mode, a spherically symmetric mode. So it turns out that the mode equation for monopoles have a pole as a function of alpha given by this. I remind you, alpha is the non-minimal coupling that enters in this operator. Remember, we are in a Schwarzschild background, so I don't care about the second coupling. So this is the only relevant non-minimal coupling that I'm interested in now. For parity odd modes or axial modes, we also have a pole now at a different value, but also depending on the parameter alpha. And for parity even perturbations, polar modes, beyond the monopole, it turns out that we have both poles in the equation, okay? We haven't done this case carefully yet. This is ongoing work, which we hope we will have out soon. So now I will just show you the results for these two cases, the monopole and the axial mode. So these are the results for the spectrum. So here there's a lot of information on this plot. So let me go slowly. So here I'm showing the quasi-normal mode frequency in the interior domain. So the trapped quasi-normal mode frequency as function of the pole distance. So here I will assume that the pole distance is in the physical domain. So I'm considering alpha to be negative and large enough so that the pole is in the physical domain. I am plotting here the fundamental mode in blue, which is, it turns out this is purely imaginary. So this is what we call a purely damped mode. So the fundamental mode, it turns out it's purely imaginary. In red, I am showing the first overtone. This is not purely imaginary. It has an imaginary part and also a real part, although it does become purely imaginary at a certain value of the pole radius. So that's one observation. And the second observation is that there is a change in sign, which is exactly what we were looking for. Remember, the sign of the imaginary part of the quasi-normal mode frequency allows you to diagnose instabilities. And the answer is yes, we do have instabilities. So the imaginary part, if we focus for simplicity on the fundamental mode, the imaginary part starts negative. Starts, I mean, for small values. So if you imagine playing with this parameter alpha, then for small enough values of the pole radius, they are stable, but then they flip sign and they become unstable. Okay, so this is what I write here, that there is a non-trivial dependence of the spectrum on the value of the pole radius. You may notice that there are some funny kind of cusps and kind of jumps here. This is because there is some kind of mode crossing that, so here I'm only showing the fundamental mode and the first overtone. It turns out, obviously, there are higher overtones. And what happens is that you actually, in some cases, you have a kind of bifurcation where some modes actually fuse into one branch. But because I'm not showing all the overtones, this looks like a cusp. It can also happen that you have a kind of mode crossing in some cases. But again, because I'm not showing all the modes, it looks as if you had some kind of cusp. So in some cases, it may be that you are simply crossing some modes. In other cases, it may be that you have a kind of bifurcation. So in our forthcoming paper, we have analyzed this in more detail, where we show many more overtones, and then that becomes more clear, okay? But that's not really important. I just want to make the comment that there is quite a non-trivial dependence on the parameters for the spectrum. I guess the main comment I wanted to make, I should have made it at the beginning. The main comment is that you will notice that there is a critical value of the pole radius below which everything is stable. So it is given by this value here. I don't know what it is, 20 something. So this actually depends on the mass of the field. So this is not a universal value. But it turns out that there is a universal combination, which is basically alpha times the mass of the field to the third power. And this does give you a universal bound for the spectrum to be stable. So this is a condition of stability for the monopole perturbation as a function of the mass of the field and the Schwarzschild radius of the black hole. So this is something we found numerically in our original paper. Later on, Hod, in a nice analysis, he was actually able to derive this analytically. So this 10 to the 10.98 that we derive numerically is actually known analytically. It's some factor of square root of 3 or so. So this was, you can look at the paper by Hod in case you're interested in the analytical derivation. Okay. So once again, we can ask whether this bound that we find here is interesting for in realistic astrophysical settings. So let me take again this example of the dark energy model. Let me assume alpha is negative, of course, so that the pole is relevant at all in this setup. And let me consider the case of a supermassive black hole, which gives me the tightest bound on the non-minimal coupling. So I will take the Schwarzschild radius to be ordered 10 to the 7 kilometers. So in this case, we can turn this into a upper bound. If you look at this inequality, I can turn this now into an upper bound on the mass of the vector field. If you remember, if you were not asleep when I was talking about the Reisner-Nordstrom black hole, you might remember that in that case, we could derive a lower bound on the mass of the vector field. So this is, I think this is nice. It's kind of a proof of concept that we can use this type of instabilities to actually not only find upper bounds or lower bounds, but actually windows of allowed parameters, and potentially maybe actually completely falsify these theories, at least in principle, using realistic values of the parameters. Another comment I wanted to make. So in this plot, what we're basically plotting is the time domain evolution. So this is just to show that everything I have said about quasi-normal modes, again, is fully consistent when you evolve in the time domain. Okay, so this shows that indeed you have instabilities in the time domain for large enough values of the pole radius. For small enough values, the modes decay exponentially in time. For large enough values, they grow exponentially in time, and we can actually confirm the numbers, and they match with the quasi-normal mode calculation. So I can offer some analytical. So all these results I have discussed so far are numerical, but we do have some analytical insight to at least gain a little bit of intuition, and in some cases, some quantitative results on these quasi-normal modes, trapped quasi-normal modes. The observation is the following: unstable trapped quasi-normal modes are roughly corresponding to bound states of the Schrödinger equation, where you consider an effective potential that's singular. Okay, so the idea is the following. Remember, we have our quasi-normal mode equation. There are some poles in the effective potential. It is easy to show that these poles are order 2 or order 1 when you write the equation in terms of the tortoise coordinate. So the insight is the following. Suppose you have a bound state in your Schrödinger problem, in the Schrödinger equation, that is deep enough inside the pole, so that the bound state actually doesn't care about any other features that you have in your potential. So generically, your potential is, of course, not going to be given by this. It's going to be quite complicated away from the pole. But the intuition is that if your bound state is deep enough inside the well, then this bound state doesn't really care about other features that you have in your potential. Therefore, your potential becomes essentially well approximated by these three terms. So this is essentially, here we have essentially a Laurent expansion of the potential about the pole. So here I should have said that, sorry. So here we have chosen the tortoise coordinates so that the pole is exactly at 0. So r star equals 0 is precisely the pole. I should have said that. So this is simply a Laurent expansion about the pole. Okay. It is not immediately obvious, but this is something you can convince yourself after a short calculation that the pole is actually order 2, and you also have powers of order 1. Okay.
Sebastian,
so now you have
roughly at 50 minutes.
Okay, I'm almost done actually. Yeah. Thanks. So now if you're teaching quantum mechanics, you can give this problem to your students actually. You can ask them, solve the Schrödinger equation with this potential. So the answer is actually no. Well, you need some special functions, so maybe not for undergrad students, but maybe as a homework problem. It turns out that you can write the Schrödinger equation for this potential as a Whittaker equation. These are some special functions, but they are well understood. And from the structure of the Whittaker equation, you can infer the spectrum analytically. So this is the result in terms of these constants v minus 2, v minus 1, and v0 of the potential. Okay, so this is the answer. So going back to the monopole perturbation of in the vector tensor theory, we can use this analytical formula to derive the following result for the quasi-normal mode frequency. So remember that there is the assumption that the bound state has to be deep enough inside the well for this whole approximation to be valid. In the case of the monopole, this translates into the requirement that this combination of the mass and the pole distance have to be large enough compared to the overtone number. So in this case, we can derive this approximation. So this explains several features that we had observed numerically indeed. For instance, it explains why, first of all, that trap quasi-normal modes, they become purely imaginary for large enough values of the pole distance. I'm thinking about this. If you go to large enough of R minus, you see that all the modes eventually become purely imaginary. So this we had observed numerically. We can confirm analytically with this formula. It also explains this linear scaling. So the quasi-normal mode frequency actually scales linearly with the pole distance. And I should also make the comment that this effect is actually not visible in the iconal approximation. So this is a nice illustration how quasi-normal modes can give you more information and more insight than just the usual iconal analysis. So I guess I'm out of time, so I will skip. Basically, what I'm going to skip is simply the results that we had for the axial modes, which are qualitatively similar. So I will skip that. So let me just summarize. I hope I convinced you that this type of non-minimal couplings are interesting. So they show up in well-motivated theories. And what we have discovered, or at least pointed out, is that they offer you what I claim to be a novel and fairly generic mechanism to destabilize black holes. I focus on black holes simply because they are kind of more clean system, but actually it also works for more general systems. We have done the analysis, for instance, for perfect fluid stars, and you can also in that setting you can also derive some interesting bounds. So you can again you can kind of reverse the question. You can ask, okay, I don't care about forming hairy black holes. I want my black holes to be stable. Then I argued that you can use these bounds to derive interesting results that are relevant for vector tensor theories. whether you think of them as useful for dark energy or maybe dark matter. So I'm thinking specifically in the case of generalized Proca theory, but as I argued, this holds more generally than that. When you look at the quasi-normal modes, we discovered this interesting new effect that we call trapped quasi-normal modes, which I have argued is it gives you a robust way to diagnose instabilities in these theories in a way that's more robust than just the usual Acorn analysis. And okay, hopefully you found this interesting, and you will stay tuned for our forthcoming papers where we generalize these to other systems. And something that's work in progress, nowhere near completion really, which is the nonlinear evolution. So we are also looking into that. So thanks a lot for your attention.
Thank you for the nice talk. Are there any questions?
Can I ask a few questions?
Sure, please.
Yeah, thank you for the interesting talk. I'm just curious, when you perturb, I just want to make sure I understand the basics. You are saying that your vector fields are perturbations on top of the Reisner-Nordstrom or Schwarzschild background. Is that right? So in other words, if nothing is happening, the vector fields are not there. But now you add them as a test field and you want to test for stability. Or do they solve,
Correct.
or they don't solve their own equations of motion at the zeroth order, or rather the answer is zero.
At zeroth order, the answer is zero, because
Okay.
I'm not considering tadpole terms. So I want the GR background to be an exact solution.
I see.
Correct.
Okay. I guess I was a little confused because at the beginning you talk about hairy black holes, but here you don't want any vector hair to begin with, right?
To begin with, no. Correct.
Okay. Okay.
Correct. So the hairy black hole is a kind of motivation. So the motivation really is to, can I reach a hairy black hole state starting from a GR state? That's the question. That's kind of the motivating question. Yes. Whether maybe you think that black holes, they start life as hairy black holes. That's fair enough. I don't know. But I think it's an interesting, at least an interesting question to ask. Okay, suppose black holes start life as GR black holes.
Right.
Can I have hairy black holes forming starting from there?
Right.
That's the motivating question.
But if they do end up hairy, it would be useful to seek solutions that are hairy as well, right? Because presumably there will be the end point of the instability.
I fully agree.
Okay.
And people and there exist some solutions actually.
Okay.
In general.
Yeah, actually that was my next question, because you say that sometimes you did find within your parameter space potential instability, right? And so actually my next question was, do you know what they will become?
No, so this is part of this question here, nonlinear evolution. This is it. Yeah, I am very interested precisely in that question. We are looking into that.
Yeah.
We are looking into that, but we don't really have results
But you did say
stage.
there are already known hairy vector black hole solutions. Is that what?
Yes.
Okay.
Yes.
And is it possible that some of them might be the end stage of what you have discovered?
I would say.
Sorry, come again. I think my connection is unstable. Sorry,
maybe that's Sebastian's connection.
Oh, is it? Okay, yeah, I was not sure because I'm I'm not sure whether it's my problem or Sebastian's issue. I still cannot hear him at all.
No, maybe he's completely gone right now. I don't know.
Oh no.
Torben?
Yes.
Oops, Sebastian is gone.
It's completely
Yeah,
gone. Is that right? Ah, okay.
yes.
Yeah, he's back.
Thank you. Yes. We can see you again. It's just
Hello,
you're still muted.
hello, hello.
Oh, yes. Welcome back.
Yes, we hear you.
I'm sorry about that. My connection, sorry. But
So you,
yes,
you were saying, I think my
so
last question to you was whether of the known solutions, hairy vector black hole solutions, do you have any clue whether maybe some of them actually point to the end stage of the instabilities that you have discovered?
I
Is there
have
any?
I have no clue. I don't think
Okay,
anybody does.
yeah.
So nobody really has evolved this in
For
numerical
for
relativity.
for example, from a black hole thermodynamic point of view, is there some kind of phase diagram that can help in this regard?
That's a good question. I have not thought about it, to be
Mm,
honest.
mm,
Yeah, I have not thought about it.
mm. Okay, okay. Uh, I guess, sorry for taking up.
That's a
Maybe,
very
maybe,
interesting question. I don't know. I don't know.
okay. Maybe one last question. I'm sorry, I always ask too many questions. The other question uh, is you mentioned Horndeski scalar. Is the Horndeski vector known? Like those most general second order vector Lagrangian. Is it known?
The most general,
Yeah,
uh, n-
Horndeski scalar is for that, right? That the most general second order equations of motion. So I'm just wondering whether the vector is known because I'm wondering whether whatever you're doing here can it be generalized to the most general second order vector?
yeah, this is a great question. I
Mm,
think the answer is not known.
mm,
So I think many people used to believe that generalized Proca was the most general,
mm,
but then people actually found new things like Proca Nuevo,
mm,
which are still second order in the
mm,
vector field.
mm.
The catch, the
Oh,
catch
yeah.
Mm,
with this generalized formalism, you
mm,
actually find higher derivatives in the Stuckelberg.
mm,
But then you have some extra constraints that actually eliminate the ghost. So the
mm,
structure of this series is quite interesting in the Stuckelberg formalism.
mm,
But if you just look at the vector field, these theories are second order, and
mm,
they are inequivalent to generalized Proca.
mm, mm, mm,
So the short answer is there is no uniqueness theorem
mm,
for vector tensor theories
mm.
as we have for scalar tensor theories.
Very interesting. Okay, okay. Thank you. Thank you very much.
Thanks.
Any other questions?
Can I ask questions?
Yeah, please.
Thank you, Sebastian, for the nice talk. So I have
Thanks.
two questions. So the first simple question is that when you show the time domain waveforms, so where is the observer? Is it asymptotic infinity?
Uh, the time domain.
Yeah, in the time domain.
No, so here we are sorry, at what value of R we are evaluating.
Yes.
I forgot this.
Is it
No, it,
far away or is it within the pole interior?
no, it is, sorry, yes, it is in the interior. Yes, it is in the interior. It is in the interior.
So outside this pole interior, you cannot see this
Uh,
exponential growth.
Correct.
Uh-huh.
So this mode is actually the boundary even though you have an instability, so the mode is growing in amplitude exponentially, you still have the boundary condition at the pole that set it to 0. So it is still 0 at the pole. So there is no communication at this order in perturbation theory with the exterior world.
Mm-hmm. I see. And
So for this, you would need to actually go beyond linear perturbation theory.
right. And the second question, I think it's a follow-up question with Ethan's previous one. So this quasi-normal mode is exponential growth are the perturbations of the Proca fields, right? And
Mm.
and then but if you want to consider, like for example, back reaction of this exponential growth to the metric, I suppose there should be some coupling, even in the linear order. There should be some couplings between these Proca fields and gravitational perturbations. So can you elaborate more on this?
Well, I think I'm not sure I got the question. I mean, I agree with what you said. I
So
don't know what the question is. Sorry.
for instance, do this Proca field perturbation coupled to axial gravitational perturbations or polar perturbations or both?
Uh, I would say the answer at the nonlinear orders, for sure you would have couplings.
Linear order, sorry.
Uh, so here so at linear order, the equation of motion for gravitational perturbations is not sourced.
Ah, really? Oh, okay.
Right. Because we are precisely considering quadratic order in the field. So this is the comment I made, that I don't want tadpoles in my theory.
I see.
Yes.
So you have to go to nonlinear level to see
Correct.
the couple. Oh, I see. Okay.
Correct. Yes.
Interesting. Thank you.
Yes. Okay. Thanks.
Okay, are there other questions? If not, maybe I can ask a question. And I mean, for some theories, you have some more exotic solutions like wormholes or something like gravity stars. Do you also can you also construct something like that in this theory?
I believe, yes, people have studied wormholes. I'm definitely not expert, for sure, in these theories. So of objects. Yes, wormholes, I believe too, at least in generalized Proca. For Proca Nuevo, very little is known. So we are actually also looking into that on a very separate kind of research direction. So Proca Nuevo is quite messy, has some kind of square root structure. So it is actually non-polynomial in the operators.
Yes, are there some other questions? If not, let me stop the recording.